great. And Stacey, yes, we can see your slides. All right, so today we're very pleased to have Dr. Stacey Alberts from University of Arizona. Dr. Alberts graduated from our very own astronomy undergraduate program in 2007 with double major in astronomy and physics. And she then went to University of Massachusetts and Amsterdam for graduate study and got her PhD in 2014. And after that, she went to Steward Observatory at the University of Arizona and has been there since. So currently, she is a research professor working on both science and instrumentation. And in particular, she works with the JWST instrumentation teams on both the mid-infrared instrument, MIRI, and also the near-infrared camera on JWST. And when she's not busy in planning for JWST observations and programs, she works on extragalactic science with a focus on star formation and AGN activity at cosmic noon. And that's what her talk is about today. Let me also advertise that Dr. Alberts is our invited speaker for this year's AstroFest on this Friday. So we'll be getting a double feature from her this week. And today she will talk about the Census of AGN at cosmic noon with an appetizer for an upcoming JWST GTO program. So please, Stacey, take it away.
Okay. Thank you so much for that introduction, and thank you for the opportunity to be speaking with you all about our latest work on AGN. I really wish I could be there in person and see campus in the spring and everything, although I've just been told it was snowing, so maybe I lucked out. So today I'll be discussing our new ultra-deep radio surveys, which we'll use in conjunction with the unique data sets in the HUDF Good South region to make progress towards a complete census of AGN at cosmic noon. And so, as was just said, this is in preparation for our JWST Cycle 1 program, where we're going to use the mid-infrared instrument to look for heavily obscured AGN, which I'll be talking about a little bit more at the end of the talk. So we'll start with our broad motivation for studying AGN. The connection between galaxies and their black holes remains one of the questions at the forefront of galaxy evolution studies. The M-sigma relation, which is seen up here, tells us that the black hole mass is connected to the structure of its host galaxy, particularly the spheroidal components, implying that the black hole's accretion history leaves a lasting imprint on the galaxy. And when we zoom out to look at global populations via the star formation rate accretion history and black hole accretion rate history, which is seen down here, we see that the shape of their evolution is remarkably similar across cosmic time, with global peaks of activity during the epoch that we call cosmic noon between redshifts 1 and 3. So despite this compelling evidence, the direct causal link between galaxy host properties and black hole growth remains elusive. Is it the feedback from AGN that regulates galaxy growth that ties the two together? This is often invoked in galaxy simulations to match the observed number counts. Or is it the common gas supply, both consumed by star formation on wide scales and also funneled down into the black hole to grow it? Maybe it's both, and there are many reasons why this remains unclear, including the vastly different physical scales between the galaxy-wide star formation and the gas content that's being funneled down to the parsec scales of the accretion disk. But today we're going to tackle the question of how to obtain a full accounting of AGN activity in statistical galaxy samples, such that we can understand the full range of AGN and host galaxy properties. So why is it so difficult to get a full accounting of AGN activity in a given galaxy population? Emission from the black hole ecosystem can affect multiple parts of the galaxy spectrum, providing multiple indications of AGN activity. Here we have an animation which illustrates how the AGN emission comes to dominate over the host emission in several features. We'll start with just a star-forming galaxy, seen here at the top in 4 different wavelengths. And down in the bottom, we see the galaxy's SED with dust features in the mid-infrared, stellar emission in the near-infrared and optical, and then X-ray emission from hot gas and X-ray binaries in the galaxy over here at the shorter wavelengths. So now we're going to turn on an AGN, and we're going to see the AGN tourist emission in red, the accretion disk emission in blue, and the X-ray emission over here in cyan pump up and start to overwhelm the galaxy's features. So you can quickly see that we overwhelm the X-ray emission coming from the galaxy and replace it with being dominated by AGN emission. We get strong continuum emission and optical emission lines from the AGN over here. And in the mid-infrared, we slowly start to pump up the infrared data, or the infrared emission from the AGN, diluting out these dust features that we used to see in the galaxy. But of course, this isn't the whole story. In the straightforward case of little to no obscuration, a luminous AGN is easily identified via excess X-ray emission line ratios or mid-infrared colors like we saw in the last plot. But now if we add dust along our line of sight, commonly from the dusty torus of the AGN itself, we change the SED. So now we're going to raise the column density of the obscuring material. And you can see that the X-ray quickly becomes attenuated such that you need to go out into the hard X-ray to identify this AGN. We lose our continuum emission in the optical and many of our emission lines, and we're kind of left with the dusty AGN torus, which is still diluting these dust features in the mid-infrared. But these features are only very diluted in the case of very luminous AGN, and with the current wavelength coverage that we have in the mid-infrared, it can be really hard to pick out these guys unless the AGN is pretty whopping. So the result is that you cannot rely on one indicator for a full census of AGN. On the left here, we see a survey of AGN in radio galaxies in the cosmos field, which were identified via their X-ray properties down here in the bottom, and their mid-infrared properties and optical to mid-infrared SED fitting. As you can see, the populations only somewhat overlap. Using just one of these indicators would result in a biased, highly incomplete sample. And even with a multi-technique approach, there is a possibility that we have an additional missing population, which we'll talk about a little bit later. So on the right, we can see another example of this. This is in the goods field, which is the field that I'm going to be talking about today. And this is the IRAC color space that's often used to identify AGN, which pop up over here in this box. And you can see from X-ray properties, the red, green, and yellow points are X-ray AGN identified, but these triangles here, the orange triangles, are AGN that are identified via their mid-infrared colors, but were not detected in the AGN. So they are detected in the X-ray. So they were too obscured to be detected in X-ray, and you needed both of these techniques to find all your AGN. So we can see the value in having both X-ray and mid-infrared if we want to look for AGN. At the beginning of the talk, however, I said that we had new radio surveys. So how can the radio help us identify AGN? As a reminder of what we typically see in the radio, we have over here a star-forming galaxy. So we have the dust peak coming down, we have free emission, and then we're quickly dominated by non-thermal synchrotron emission from supernova remnants as we get down to lower frequencies. So below frequencies of about 10 or so, we have this kind of canonical slope of -0.7 or so in local galaxies, or maybe about -1 in more Euler type galaxies and high redshift galaxies. So we can use the radio in a couple ways to find AGN. The most spectacular, of course, is just looking for kiloparsec scale jets, which are seen beautifully in local galaxies and can actually even be seen sometimes in high resolution radio imaging out to high redshift. So AGN that have these nice jets are called jetted AGN or radio loud AGN, as I will refer to them throughout this talk. But obvious jets are not really representative of the radio loud population, and so we need another way to identify them. And most of the time we do that by looking for excess radio emission relative to other wavelengths. So down here we have the Q24 parameter. So this is looking at the emission coming out at 24 microns versus 1.4 gigahertz. And in star-forming galaxies, these both trace the emission from young stellar objects, with 24 micron coming from light reprocessed by dust, and the radio coming from supernova remnants. And so these form what's called the radio infrared correlation, which is just kind of a nice correlation. It changes a little bit with redshift, but the correlation does hold as a function of redshift and is very good for identifying star-forming galaxies. Now in AGN, both 24 microns and the 1.4 gigahertz can contain emission from AGN, but in these radio loud AGN, they really stand out as outliers. So you take your radio infrared correlation, find your outliers, and these are your jetted or radio loud AGN. But radio loud AGN are actually, in fact, just the tip of the iceberg, and they comprise about 10% of AGN in general, becoming more prominent at higher radio luminosities. The remaining AGN are called the so-called radio quiet AGN. And so this group encompasses two subgroups of radio emission. You have AGN where the radio is solely being powered by star formation, and you have to identify the AGN via other means. And then you have AGN where the radio is a hybrid mix of star formation and AGN emission, a situation which has been confirmed to exist with some local high resolution interferometric studies. But separating these two cases in a given galaxy is not very easy. And it's not easy to identify these AGN in the first place. You have to go to other wavelengths, such as the X-ray or the mid-infrared, as we saw earlier. Multiband radio data, however, can be used to identify AGN in the case of a compact radio core. So for these AGN, the nucleus is dense enough that it experiences synchrotron self-absorption, producing a flatter slope than the canonical slope that you would expect from synchrotron happening from star formation. So if you have multiband radio data, which I do, you can look for flat slopes as another indication in the radio for AGN activity. Okay, so that brings us to our new surveys. So these surveys are in the Good South HUDF region, where we have some of the deepest X-ray available, 7 megaseconds of Chandra X-ray imaging, plus the deep candles photometry in the optical and out to Spitzer and Herschel in the infrared. And now to add to this, we have obtained 6 gigahertz and 3 gigahertz radio imaging, both over a small area. So the 6 gigahertz beam is this guy, 3 gigahertz beam is this guy, whoops, over a larger area. But today we're just going to be talking about the area where they're shared so that we can take advantage of this multiband radio data. And this, to place our surveys in the context of other radio surveys, we are going deeper, although over a small area. And nicely, we are going deep enough to be picking up the same galaxies that the super deep X-ray data is picking up. So here's our 6 in our 3 gigahertz survey. And then I wanted to note here that the Cosmos field has a similarly deep 3 gigahertz survey. And I'll be comparing a little bit to their results later. Okay, so we were interested in making full use of our multiband radio data. So we restricted our sample to the overlapping region between 6 and 3 gigahertz, which is about an area of about 42 square arc minutes. So it's not huge. And we identified 100 radio sources kind of at cosmic noon. We wanted to stick to cosmic noon because that's the focus of our JWST program. And they all have, we matched them to 3D HST and Spitzer counterparts so that we have the full optical to mid-infrared coverage. So as you can see over here, our sample is mostly galaxies, 10 to the 10 to 10 to the 11 solar masses. And so they're kind of typical main sequence star-forming galaxies. So using this radio sample, we're now going to pretty much just try and find as many AGN as we possibly can. So we start with the ultra-deep 7 megaseconds Chandra X-ray imaging, which very crucially is complete down to luminosities of about 10 to the 42 ergs per second. So this depth is really nice because it gets us into the regime of more normal type AGN called Seaford type AGN. But it's also around where the X-ray emission from the most vigorous star formation peaks. So this is around the region where it gets ambiguous whether you could have X-ray emission coming from star formation or X-ray emission coming from AGN. So anything above, say, 3 times 10 to the 42 ergs per second, which is this line here, we're pretty much sure that this comes from an AGN because star formation can't produce this much X-ray. So in this plot here, we're looking at the intrinsic X-ray luminosity as a function of our 6 gigahertz luminosity. And as I said, we've identified AGN in these sources because they have too much X-ray emission. We also look at their X-ray spectrum if multiband X-ray data is available. And so these guys here in the blue have a hard X-ray spectrum, which is indicating that they have obscured AGN emission. And then we can start to try and push down below this line by comparing the X-ray that's coming from these galaxies to the X-ray from other wavelengths, such as in the optical, the infrared, and the radio. And we'll be talking about that a little bit more. Oh, and I guess I should say that these guys are galaxies that have X-ray emission, but not enough, no indication of AGN. And then you can see that a lot of our sources are not actually detected in the X-ray.
Casey?
Yeah.
So if you go back to the previous slide, so you said you use that horizontal dotted line as the cut to select confidently the AGN
Yes.
because the X luminosity. But the others are some purple points below that line, which you still call X-ray AGN. Is that based on optical spectroscopy?
So no, these guys right here are also X-ray selected AGN, and they are selected as AGN because they have elevated X-ray relative to other wavelengths. So this is, and I'm going to talk about this a little bit more. So we basically compare it to the infrared output to say how much star formation the galaxy has, and then we say, oh, there's still a lot of excess X-ray in this galaxy, so it has to be coming from an AGN.
Got it. Okay, thanks.
Okay, so that's our X-ray AGN selection. We next want to turn to the mid-infrared to look for mid-infrared's excess sources. And we do this using the standard IRAC color diagrams that we saw earlier. And we do this through the optical to mid-infrared SED fitting because we have all this really, really nice photometry. So the reason you want to do this, of course, is because some AGN don't show up in the X-ray because they're too obscured and they can pop out in the mid-infrared. So we're using here 3D HST and Spitzer photometry, and we have the MIPS point over here. And we're fitting all of our galaxies to a couple of representative templates. So we have star-forming galaxies templates, which are shown here in the blue. We have templates representing stellar emission, and then we add an optional AGN with attenuation on top. Sorry, it's allergy season here, so my throat is very dry. So there's complications to doing this with the data sets that we have. One is that just the data set is sparse, and so it's pretty hard to pick up on mid-infrared AGN with the data that we have here. And I'll show what I mean with that in the next slide. And additionally, we have to kind of limit the number of free parameters we have based on this data. And so we're limiting ourselves to just type 1 AGN templates plus attenuation. We would ideally like to add type 2 templates in as well, but the type 2 models are kind of all over the place. They cover so much parameter space and they're kind of uncertain. So we just didn't feel like it was supported by our data to be able to fit all that. So to be confident what we found in AGN via this technique, we fit all our sources with galaxy templates first, and then add in the AGN template. And then we use an F-test to determine whether the addition of the AGN template actually improves the fit. And we require a 93% confidence that it improves the fit in order to call something a mid-infrared excess AGN. Okay, and so here in this example, I've been showing one where the addition of an AGN does help. So you can see kind of when you come out to this IRAC, the IRAC bands here, the galaxy-only models are not really fitting. We need some more emission to fill in this stellar minimum here, and that's where the AGN comes in and fills it in. But really what you would want is the data that's missing here by the gap in the between IRAC and MIPS. And of course, that's where JWST is going to really help us out. Okay. So now we can take our mid-infrared identified AGN and update our X-ray versus radio plot. So that's what we've done here. These orange diamonds now are AGN that have been identified both through their X-ray and their mid-infrared properties. And then the red circles are new AGN that have been identified via their SED fitting and not their X-ray properties. They're not X-ray detected. And so there's only 3 of them. You can see there might be 4, there might be 1 missing in the back. But there's very few. And we can go back and we can compare this to what we looked at in Cosmos earlier when they found nearly half of their sample through mid-infrared excess and the other half through X-ray AGN. So we're finding a lot of our AGN more through X-ray properties. And I think that this is most likely because our X-ray is just incredibly deep and incredibly complete down by this 10 to the 42 ergs per second limit. And so we're really able to pick up on a lot more AGN activity that way. For contrast, the Cosmos field has about half as much X-ray depth. So in fact, we can push this combination of ultra-deep X-ray and radio data even a little bit further. So in star-forming galaxies without AGN, you can imagine that the X-ray and the radio, both tracing processes related to young star formation, are in fact correlated. And so, as I mentioned earlier, radio quiet AGN can have most or all of their star formation coming just, or sorry, most or all of their emission coming just from star formation. And so this allows us to look for excess X-ray from AGN activity above the radio, what the radio is telling us about the star formation. So that was the question that we had just a little bit ago. And so we've done this by taking the X-ray to radio relation for star-forming galaxies, and in fact, the relation for a maximal starburst. So if you pump up your starburst in your galaxy, you're going to have kind of a relationship between your X-ray and your radio that's over here. And then we said, okay, we're going to go 5 times that, and we're going to call anything above this an outlier in terms of its X-ray emission, and that's probably has to come from an AGN. So using this technique and this super deep X-ray and radio, we were able to find 10 more candidates for AGN for our sample. Okay. So what else can we get from the radio data? Even though our radio imaging is high enough resolution to see large-scale jets, there were none in our sample. This is not unexpected because they're pretty rare. So in order to identify radio loud AGN via the radio properties, we're going to use Q24. So here you see our full radio sample. In the background here in the dashed lines, we've taken star-forming galaxy templates at a range of luminosities, and we've looked at their Q24 as a function of redshift. So that's what the lines in the back, and then the scatter that we expect is the gray shaded region. And then on top, we put all our radio galaxies. And as you can see, most of them scatter around the radio infrared correlation. In order to identify outliers, we then say, okay, if you're 0.5 dex below this relation, you're probably an outlier. And so we pick up on a few radio loud AGN this way. And in fact, you can see that a couple of them were previously identified as galaxies because they were just little gray circles. There's not that many of them. That's okay. We don't expect that many of them. About 10% of AGN are radio loud. And so we're kind of right in line with that, even though we're looking at a pretty faint radio population. Okay, and then I mentioned our other radio indicator, which takes advantage of our multi-band radio survey, is looking for a flat spectrum. So here, again, I'm showing a star-forming galaxy with its canonical synchrotron slope, and then you can see the slope of all our radio galaxies kind of plotted over it. So there's quite a variety. So we plotted them up over here as a function of redshift. We're finding an average of -1, which is kind of in line with some other high redshift galaxies or high redshift radio studies. And then anything above this line has what we would call a flat or inverted radial slope that probably is coming from synchrotron self-absorption. There's not a lot of other mechanisms that can flatten out the slope like that at these frequencies. And so these guys are candidates for AGN, anything above this line in the shaded region. So there's 4 of them 5 of them that we had previously identified as AGN via other methods. So we're pretty confident about those. And then there's 2 additional candidates that were not identified previously. And so those are maybe a little bit more tentative. But I should mention that at the beginning of talk, I said that our 3 gigahertz data is a little bit shallower than our 6 gigahertz data. That, of course, will bias us against these flat slopes. Luckily, we are actually going to get similarly deep 3 gigahertz data. In fact, the catalog was just completed yesterday, so I get to start digging into this soon and figuring out how many of the quarter of our sample that were not detected at 3 gigahertz might have a flat slope. In the meantime, I had stacked them. So it's about 25 sources that were not detected at 3 gigahertz that were detected at 6 gigahertz. And I stacked them and looked at their slope. And as you can see, it's up here in this shaded region. And so we probably have a lot more, or at least some, more flat spectrum sources, which are candidate AGN in this stack. And I'll be able to pull those out pretty shortly because we're ready to go with that data. But for now, we find a lower limit of about 15% of our AGN have this flat radio spectra. From comparably faint radio studies, a little bit brighter than ours, but still pretty faint, they find fractions of 30 to 40%. So we're, maybe when we disentangle this stack here, oops, we will find up to that 30 or 40%. And the nice thing is that recent modeling with the SKA predictions have shown that the radio number counts would be better reproduced with the introduction of increasing core fractions at fainter radio fluxes. So that would indicate that in faint radio surveys like ours, we should find more of these compact radio cores and this synchrotron self-absorption. So this is kind of, if this pans out, it might work really well with some of these predictions. And then of course, when we get the next generation facilities, the NGBLA and SKA, this might be a really nice way of looking for AGN in general. Okay, so at this point, we have identified AGN in radio galaxies using X-ray, mid-infrared, and radio indicators. And we found, as expected, that most of our radio AGN are radio quiet. However, it's ambiguous in our sample whether the radio is being powered purely by star formation or by a hybrid of star formation and AGN activity. So to explore this issue further, we did a little side calculation based on a sample of radio quiet quasars at redshift 1 from White et al. 2017. So these quasars are bright AGN that are pretty much swamping out their host galaxies, and they have measurements at 24 microns, at 160 microns, and at 1.4 gigahertz. So in these bright quasars, the 24 micron and the 1.4 gigahertz are expected to be dominated by the AGN, and White et al. Was able to show that the radio was dominated at least at the 80% level on average in these galaxies. But the 160 micron is out there at the top of the dust peak, and so it is tracing just star formation. The AGN shouldn't be affecting that wavelength too much. So what we did was we looked at the ratio. So we took a typical star-forming galaxy and we looked at the ratio of 160 to 24. And for star formation, it should be around 60. And then we looked at the sample and we used the 160 micron and the 24 micron together to subtract out the star forming component, assuming this ratio, from the 24 micron that they were measuring. And so what we're left with is kind of a Q24 just for the AGN component, with this star formation corrected 24 microns from the AGN, and then the radio emission from the AGN as well. And so you get this a factor of 1.8. And if we compare that to the Q24 for star formation, which is a factor of about 1, we find that it's at fixed infrared output, radio output from the radio quiet AGN is expected to be about 5 times weaker than that from star formation. So this is about a factor of 5 weaker, and this is in this weird log space. But basically what we're saying is that in galaxies in AGN that are not swamping out their host galaxies like these quasars, in more normal AGN like the ones that we're looking at, the contribution to the radio from the AGN is actually expected to be pretty weak relative to the star formation. So to check this, we went and we pulled the 160 micron data for our radio sample. Now, unfortunately, our radio sample is faint enough that only half of the sample is detected at 160 microns due to the reduced sensitivity and confusion limit of Herschel. So we have upper limits for the other half. But we took a representative star-forming galaxy template again, and we looked at its Q160 parameter now. So that's the relationship between 160 and its radio. And then we subtracted off what we were observing in our sources, and you can see that this is the scatter expected for star-forming galaxies, and all of our sample pretty much just falls within that scattered region, which is what you would expect if all of the radio is more or less being powered by star formation. But I should say, okay. So this is saying that our radio sample is consistent with the radio emission being powered by star formation, except there might be some in these upper limits where you say, oh, well, they would scatter up here into the AGN area. And in fact, that's probably what's happening with our radio loud ones, which were denoted by the crosses here. So they would probably be up here in the AGN output. But the 160 micron is not, whether or not it's detected at 160 micron is not expected to depend on the AGN at all. So we don't really think that there's a lot of other AGN sneaking by in these upper limits. And so probably most of our sample is being powered by star formation in the radio, except for maybe these flat spectrum sources. So of course we've seen that something is flattening out their spectra. It's probably the AGN, and so the AGN is having some influence on the radio emission, and yet they're kind of still falling in this scattered area within the radio infrared correlation. So that's kind of a mystery. Maybe these are true hybrid sources, which the radio is being powered by star formation and AGN, but it's still really hard to disentangle that. And I don't think this mystery has been solved. We do have clues from local studies and very high resolution studies on a handful of radio quiet AGN at higher redshifts. And so there's studies like from the Australian long baseline array where they have found milliarc-second structures in the cores of galaxies. And so these cores are compact radio cores from radio quiet AGN. And they find that, you know, maybe 50%, maybe a little bit more is being powered by the AGN as opposed to star formation. But it's really hard for us to know how common these are. And of course, it's kind of hard to pick them out using the radio infrared correlation because they could be increasing the scatter in that relation. Yeah, and so there's a lot to disentangle here. This is just one example from one of the studies. There's a couple of studies recently, but there's really only a handful of AGN in these studies because, of course, getting these high resolution observations is very expensive. So we just don't know at this point. Maybe these flat spectrum sources are a clue as to how often this hybrid situation happens, but I think it requires further study.
Stacey?
Yeah.
Another question. Sorry to interrupt. So if you go back one slide,
yeah.
When they do those long long baseline in the high resolution radio imaging, is the radio flux that you detect for those systems mostly coming from those compact cores, or are they missing extended radio flux?
They are missing some extended. If I recall, it was usually about 70%. They were picking up on 70% of the total emission that was picked up with lower resolution studies. So yes, they are missing some extended components. Yeah, it varied. I mean, we're really talking about a handful of sources here. So there were some cases where it was like 50-50, some cases where it seemed to be 70. It was just kind of all over the place. But yes, they are missing the extended component.
Okay, good. But at least a significant fraction of the radio flux is coming from the AGN.
Yes, and I think we're a little bit biased towards that situation. You know, I mean, it would be harder for us to observe the ones where it's like 30%. But sure. They probably exist, right?
Yeah, it's a selection bias.
Yeah. Okay, so let's pause here and sum up what we've found so far. So using our three main identification techniques, we've identified AGN in about half of our radio population. We found 51 AGN out of 100 radio sources. Most of these AGN were indicated in the X-ray, which I think is really thanks to this ultra-deep 7 megaseconds radio imaging, or X-ray imaging, sorry. About 10% of our sources are radio loud, which is consistent with other slightly brighter samples and kind of what we would expect. And then we found 15% or so have this flat radio spectrum. But of course, that's a lower limit because we're going to be getting deeper 3 gigahertz data. So that's kind of TBD. But wait, we have been looking for all the AGN that we could possibly find. And of course, we biased ourselves right from the beginning by requiring this to be a radio selected sample. So now we went and we looked for what we might be missing and compiled a list of X-ray selected AGN within the same redshift range, so around cosmic noon, that have 3D HST counterparts so that we're doing a fair comparison to our radio sample. And when we did that, we found nearly an equal number of AGN among the radio undetected sources as among our radio sample. We didn't do a full SED analysis to find the MidInfrared Excess ones that we might be missing. So we might be missing a few more. But as we saw earlier, the X-ray data is really picking up on a lot of the AGN. So basically, we've doubled our sample of AGN by looking for that. And I think that's just what it says here. Yeah. Okay. So that's actually a lot of AGN. 50% within the radio sample is a lot. And then we double that number just from looking at X-ray selected. And that's actually a little bit weird. So I mentioned earlier in the talk that the Cosmos teams have now got a 3 gigahertz sample. Their paper came out a little bit after mine, I think. So they have 3 gigahertz selected sample down to similar depths, although lower resolution, but over a larger area because they're looking at the whole 3 gigahertz beam, which we will be looking at with our deep data shortly. So they have 350 square arc minutes to our 42. And they did AGN selections in a slightly different way. They mostly looked for X-ray excess over the total infrared luminosity, which is of course tracing star formation. They did the mid-infrared and SED coloring, SED fitting techniques. They didn't have the multiband radio data, so they didn't do that. And then again, to remind you, they have about 4.6 megaseconds versus our 7, so the X-ray is a little bit shallower. They found 23% of their radio sample had evidence for an AGN versus our 51. So that's actually pretty interesting. Could be cosmic variance. It could be that we have a small field with small number statistics, but I really think it's going to come down to the deeper radio data, or deeper X-ray data. I keep doing that. The deeper X-ray data, which I think is really important. And so we're going to soon have comparably deep and wide 3 gigahertz data for good south for a more direct comparison. And we're going to go through and we're going to redo all of this analysis to find as many AGNs we can in the larger 3 gigahertz footprint. And then we'll have these two fields to compare and see if they're just very different from each other, or maybe the 7 megaseconds X-ray is really making a difference. Okay, so for our final topic, I wanted to talk about AGN that might still be missing from our census. So these would be heavily obscured in Compton Thick AGN, which remain notoriously elusive in basically every way we look for them. So to be detected in the X-ray, we need deep hardband X-ray data. And there are degeneracies between the obscuration and reflection component in the X-ray SED, which makes identification kind of tricky. So in general, the fraction of Compton Thick AGN, both from local studies and more high redshift, is usually set somewhere between 10 and 50%, which is not very certain. We'd really like to be able to narrow this down. And of course, in the mid-infrared, we look for obscured AGN that don't pop out in the X-ray. But with the current data that we have, we're usually limited to just the most luminous AGN. And so there could be a lot of guys that we are still missing. So first, I wanted to say how many obscured AGN do we think we have in our sample with the data that we do have. So this is showing you the intrinsic X-ray luminosity as a function of now the 6 micron, not 6 gigahertz, but 6 micron luminosity of our sources. And so these in unobscured type 1 AGN, these two will be nicely correlated and they should fall around this line here. And then if we add enough obscuring column or absorbing column to make a Compton Thick AGN, this line would move down here to the dashed line. And so anything that falls below this dashed line in this relationship is probably a pretty heavily obscured AGN. So actually about 30% of our AGN candidates fall below this line, thanks to the various ways we have to look for obscured AGN, the hard X-ray and the mid-infrared. And so we're already kind of falling in the middle of this predicted fraction here. But we could still be missing some. And if there are more, well, then how will we find them? So looking at the SwiftBat hard X-ray samples for local AGN, we noticed that heavily obscured AGN kind of roughly fall into maybe a bimodal distribution. So on the one hand, you have the edge-on cases, which is kind of the type 2 AGN that you typically think about, where you're just looking along the line of sight directly into the torus and have just all this obscuring material along your line of sight. But there's probably another case, which is when the AGN is just so embedded in the core of the galaxy that the absorption and re-emission of the AGN emission into the infrared is more isotropic, pumping up the infrared continuum, but otherwise leaving a featureless, fairly featureless spectrum. And so I can show you two local examples of this. So here we have NGC 5428, which is a typical type 2. So you can see the dust features in the mid-infrared. There's mid-infrared forbidden emission lines, some of which are high enough ionization that they have to be coming from the AGN output, which would be really nice for JWST spectroscopy. But pretty much you get kind of a, lots of features in here. And then when you go over to the embedded case, we have an example like Markarian 231, where you see everything is kind of been thermalized in the mid-infrared. We just have a featureless black body spectrum with radiative transfer effects. And we've kind of lost lost our AGN forbidden lines, we've lost our dust features, and we're kind of just left with this like featureless spectrum. So how will these AGN reveal themselves? So in both cases, the X-ray and the optical emission line signatures will be heavily attenuated and largely unavailable. But we can look at the rest 3 to 5 micron region to look for mid-infrared excess, which is kind of the region that we were looking in before, but we didn't have a lot of data to actually cover it. And so why does this work? So in star-forming galaxy, this region is a minimum in the stellar emission. So you can see that over here in this SED. The blue SED is a star-forming galaxy. There's kind of this minimum in stellar emission that's pretty ubiquitous among massive galaxies. And very nicely, this region also happens to be a minimum in terms of the optical depth, kind of along the same lines as hard X-ray. So hard X-ray, this is silicate dust, the optical depth of silicate dust over here. And here's your hard X-ray. And so you're sitting in kind of a minimum of the extinction. And here's your 3 to 5 micron region, also in a pretty competitive minimum in the extinction. And so looking for this mid-infrared excess should be pretty competitive with looking for hard X-rays. And so we can see that here in an example. So this is WISE photometry of a local galaxy, NGC 4945, which is known to have an X-ray attenuation factor of about 30 to 40. But when we take its WISE photometry, which is these 3 orange points, and we put it over in comparison to a star-forming galaxy, you can see that the emission in the 3 to 5 micron region just basically fills in this minimum very nicely. The AGN just pops out, no matter how obscured it is. And the nice thing about JWST is, of course, these are the mid-infrared filters, and they cover this region very nicely over the regime of cosmic noon. So that's what I'm just showing here. Redshift 1 up to redshift 2.5. You start to lose your dust features and whatnot out of the MIRI filters, but we can cover this minimum pretty nicely and look for AGN across cosmic noon through this mid-infrared excess. So this contrasts with the IRAC colors that we've been using. So having this coverage of the 3 to 5 micron region, plus a probe of the aromatic features, really allows us to push past the luminous AGN barrier that we had with the Spitzer IRAC colors into regimes of both lower luminosity AGN and the composite regime, excuse me, where the AGN fraction in the mid-infrared might be less, might be 50% or even less. And so to illustrate this, so we did a study using galaxies that had Spitzer IRS, so that was Spitzer spectroscopy of their mid-infrared spectra. And we used templates derived from that in addition to candle spectrometry to simulate AGN and composite galaxies in mid-infrared, in MIRI color space. So here you can see if you have 4 bands, you're kind of restricted, you really want to cover certain features like the minimum here and cover over here on the aromatic bands. So if you have 4 bands, you can cover like a little bit of redshift space pretty nicely and create your IRAC color diagrams, except for MIRI, with your AGN popping up over here in this space, composites here, and then your star-forming galaxies off in this space. And if you use 6 bands, then you can do this basically from redshift 1 to maybe 2.5 over cosmic noon. So we predicted that galaxies with solar masses of 10 to the 10 or more would have completenesses and reliabilities around 70 to 80% using these color diagrams with what we currently know. Hopefully that JWST will be revealing more about the mid-infrared spectra of galaxies, and so we'll be able to refine these color selections. Okay. So for heavily obscured and Compton Thick AGN specifically, we did some more back of the envelope calculations using local galaxies like Markarian 233 or 231 as a prototype. And so now we're going to put things in terms of the Eddington ratio, which is the ratio between the AGN's bolometric luminosity and its maximal accretion. And so with this, we can predict that we should be detecting absorbed obscured AGN, so the Markarian 231-like spectra, down to pretty low Eddington ratios of 0.03%, which is, the C for galaxy regime. For type 2s, you do a little bit worse. You're only getting down to Eddington ratios of 1%, which is still really, really good. And so we really think that we'll be able to find the heavily obscured and Compton thick AGN that might have been missing all this time with this technique. In terms of the total number of AGN we expect to find, for galaxies above 10 to the 10 solar masses, we expect from our survey, from our radio survey, about 6 AGN per MIRI field of view at cosmic noon in good south. And then, of course, plus the additional Compton thick and composites that we might be currently missing with our selection techniques. On the right here, we see the 10 micron number counts predicted for the Cosmos and Candles fields in Kirkpatrick 2017, where we did a study of the populations broken up by Eddington ratio again. So the AGN here are here in this goldish color. The composites are here in this more purple color. And you can see that this this agrees nicely. I think we're saying around 10 galaxies per MIRI field of view, which agrees nicely with the 6 that we predicted over here. And that's, of course, for massive galaxies, and these number counts are rising very steeply. So you might say, well, we're going to get even more with low mass galaxies. And of course, that will be super awesome. But once we get into the low mass regime, we need to be a little bit careful because low metallicity effects can come into play. They might add hot dust to the rest 3 to 5 micron region. And they might also dilute out the aromatic bands through grain destruction. And so we're going to have to, adjust our models and our color selections once we understand a little bit more about what low mass galaxies look like in the mid-infrared part of the spectrum, which JWST will be able to do for us. So that'll be fun. Okay, so I'll close with a preview of our GTO survey in the HUDF. I've discussed so far the value of looking for the excess emission at 3 to 5 microns. But of course, there are other ways that JWST will be invaluable in finding AGN. In addition to looking for mid-infrared excess, we can look for weak aromatic bands. There are other things that can weaken the aromatic bands, so we've got to be a little bit careful there, but that will be valuable. And then we can also look for mid-infrared variability between the Spitzer data that exists now and the mirroring data that will cover, a different epoch. And I will direct you to our postdoc, John Way, has a really nice paper for further details if you're interested in mid-infrared variability. And so, of course, this imaging is going to be really great in finding large samples of AGN candidates, but we're going to want to check our techniques with spectroscopy. So that's where NIRSpec is going to come in. NIRSpec and actually NIRCam imaging can be helpful here too. NIRSpec will cover several new features, key features. We have the Passion Alpha, the Passion Beta, and the Helium-1 line. So normally when we look for obscured AGN, we look for broad line components on the optical emission lines, but with your typical H alpha, H beta, the obscuration, basically gets rid of your broad line component. We have less obscuration in these lines here, so we have a better chance of looking for those, finding those broad wings. There is a weak there's a CO absorption feature from red giants and other stellar features at wavelengths of about 2.3 microns, which can be weakened or diluted by the presence of an AGN. So that's another thing that we can look for. And then, of course, we will have the typical optical line ratios for many, many more galaxies and across many a broader redshift range than we previously did with JWST spectroscopy. Okay, so I'm just going to show a couple. So the HUDF and Good South region is basically the target of a ton of GTO data. This is the JWST Advanced Deep Extragalactic Survey. So this is over 900 hours of observing time with NIRCam and NIRSpec. So this is just kind of showing the layout of the field. Whoops, my little HUDF got moved. But this part right here is the HUDF. Here's the Candles field. And we're basically covering, this is extremely deep NIRCam photometry, a medium NIRCam photometry field, and then a bunch of parallel data. And then this will all be covered with NIRSpec as well. And the JADES program, and we have some MIRI, really deep MIRI parallels, which will be fun too. And the JADES program is pretty much aimed at higher redshift science, not the AGN stuff that we've been talking about. So that is where our survey comes in. So this is the MIRI HUDF survey led by the UA MIRI team. And so we are going to do 15 pointings of MIRI covering 30 square arc minutes in all of the MIRI bands, covering this really deep NIRCam data. So of course we'll have NIRCam and NIRSpec as well. We have some of our own NIRSpec follow-up just dedicated to looking for and confirming these AGNs that we're going to be getting candidates of. And so this gives us a really nice handle on trying to find these heavily obscured AGNs through all the techniques that I just outlined. And so we are aiming our depths at high significance for a Markarian 231 type AGN with a bolometric luminosity of about 10 to the 10 solar masses at redshift 1, or I'm sorry, 1% of the brightness at redshift 1 and 10% of the brightness at redshift 2. So yeah, we're going to find these heavily obscured AGN. Okay, so this is my conclusions. AGN are everywhere. We found tons of them in our faint radio sources, reaching down to galaxies on the main sequence. If you want to find all the AGN, you need a multi-wavelength approach. And definitely I would say that you need the ultra-deep X-ray imaging. That is really, really crucial. This multi-band radio, though, is a really useful tool for identifying AGN, and it might be really useful in faint radio populations, especially with next generation facilities that are coming. And then still unknown is the heavily obscured and Compton Thick AGN fraction. Do we have a lot of these edge-on and absorbed cases out there at cosmic noon? JWST MIRI, we're going to find them. So yeah, thank you.
All right, thank you, Stacey. It's a nice talk. Do we have questions from the audience? Please raise your hand. Yes, Brian.
Yeah, so Stacey, thanks. Great to see you again, and thanks for your talk. It was very impressive stuff, and for everyone else, all the more impressive because I looked it up. Stacey took 406 from me, so you know she managed to do great work on galaxies despite that. So I'm interested in sort of the bottom line, the kind of population results. So the kind of hand wavy thing I probably said in 406 is, oh, maybe all galaxies have an AGN phase. And if so, with your population, you could get an idea of how long that phase is. So first, is that a dumb thing to say? And if it's not, do we have a sense of how long the duty cycle of this phase would be?
I don't think it's a dumb thing to say, and I think that we're hopefully going to be getting at that more with our mid-infrared variability studies and variability studies in general. I don't know if there's anything that I can say specifically about this sample and that. I feel like we're not quite there yet. I mean, this is only a sample of 100 galaxies, and we're just trying to find all the AGN to begin with. It is something definitely that we should keep in mind when we go to our larger 3 gigahertz sample and potentially combine it with the Cosmos sample so that we have better number statistics.
Cool, great, something to look forward to. Thanks.
So Stacey, I have a general question about those embedded AGN that you were talking about.
Yeah.
So it appears that the MidInfrared Excess would be the most efficient way to identify them because they don't pop up in other methods. So to my knowledge, it might be wrong. So correct me if I'm wrong. There are not many known cases where the AGN is only selected by MidInfrared Excess, but all the other diagnostics like X-ray, forbidden lines, and optical spectroscopy all failed. And there are probably only a few of them, and people claim that those are probably heavily embedded, like in a cocoon of dust, where you can only use mid-infrared color to select those objects. And by the way, they are potentially also Compton thick, so X-ray would also not be very efficient. I wonder what is your general feeling about this class of heavily obscure, like cocoon AGN, and do you have data to, for example, in the good south, to look at their HST morphology, are they emergers, compared to the rest of the normal AGN you select with other methods?
I wonder if okay, yeah. Well, so to answer the second part first, this is the morphological breakdown between the galaxies in our sample and the AGN in our sample, and it's basically the same. There was no indication for more mergers or irregulars. Of course, this is all based on the visual classification that was done in the Good South field with HST data, which is really good for what we can do now. This is definitely something I want to do with NIRCam data, because NIRCam will be able to look at longer wavelengths with more with HST-like resolution, which might be a little bit better for looking at morphologies and mergers and stuff. But at the moment, it doesn't look like there's much to say about like the merger rate. Mm-hmm. Your first question, so I don't really know. I don't really have a great sense of what we should expect with these embedded cases, because I feel like except for the X-ray, I mean, they definitely, a lot of them don't stick out in the X-ray, and they probably are, heavily obscured in the X-ray. I feel like we don't have the completeness in terms of optical spectroscopy and mid-infrared spectroscopy to really say whether these are everywhere and not popping out anywhere except for the 3 to 5 micron region, or if they do have other indicators, we're just not looking at large enough samples.
Mm-hmm. Yes, I guess that's a fair statement. Once you have enough of these objects selected with JWST imaging from the infrared, and will be able to look at the other wavelengths and to and hopefully we'll be able to look at some lines that are less extincted, like the Paschen alpha lines, and get more of a physical understanding of what's going on with these sources. Right. Thanks. Okay. Any more questions?
So I joined a little bit late, Stacey, but thank you again for giving this talk. Maybe you talk a little bit about what sort of variability information you can get from these observations, in particular for things like tidal disruption events. What sort of signals should we expect to see in these JWST observations, just incidentally, that happen to be in the field at the same time?
I think that's a better question for Decker. I haven't really thought about tidal disruption events too much at these redshifts. Isn't that really hard?
I have no idea what to expect. So if you could, maybe somebody at your end had actually done some studies on what we might find serendipitously.
We haven't thought about that too much for our cosmic nude study. It's definitely something I probably should think about a little bit about more, but I just kind of assumed that it was too hard.
Maybe you get lucky. Have to be well, the rates is pretty low, and especially with your small field. But I think Gautam, Stacey was mostly referring to aging variability for the mid-infrared pandemic stuff. But TDE might,
Yeah, I'm just curious as to if there's anything we should just serendipitously expect in the same fields, and how would we go about looking for stuff like that?
No, that's a really good question, because now I'm worried that we're going to be mistaking mid-infrared variability signals for something else. Although maybe we have enough epochs. I mean, maybe not in Good South, but there is the North Ecliptic field. I've forgotten the other name for it now. There's the continuous viewing zone of JWST, where we're just going to be getting epochs and epochs and epochs of and that'll be a great place to look for these recurring signals from AGN and try and get more of a handle on the duty cycle and how regular they are, and then maybe look for these serendipitous tidal disruption events.
Cool, thanks.
All right, let me check if there are more questions in the audience. Okay, if not, let's give Stacey another round of virtual applause. Thank you very much. Oh yeah, Brian, you have a question afterwards. So yeah, Brian, feel free to stay on, and everyone else, if you had to leave, feel free to leave. Thanks, Stacey.
Thank you.